About two-fifths of all the water that gets withdrawn from lakes, rivers, and wells in the US is used not for agriculture, drinking, or sanitation, but to cool the power plants that provide electricity from fossil fuels or nuclear power. Over 65% of these plants use evaporative cooling, leading to huge white plumes that billow from their cooling towers, which can be a nuisance and in some cases even contribute to dangerous driving conditions. Now, a small company based on technology recently developed at MIT by the Varanasi Research Group is hoping to reduce both the water needs at these plants and the resultant plumes, and to potentially help alleviate water shortages in areas where power plants put pressure on local water systems. The technology is surprisingly simple in principle, but developing it to the point where it can now be tested at full scale on industrial plants was a more complex proposition that record the real-world experience that the company's founders gained from installing prototype systems, first on MIT's natural gas-powered cogeneration plant and then on MIT's nuclear research reactor. In this demanding test, which involved exposure to not only the heat and vibrations of a working industrial plant, but also the rigors of New England winters, the system proved its effectiveness at both eliminating the vapor plume and recapturing water. And it purified the water in the process so that it was 100 times cleaner than the incoming cooling water. The system is now being prepared for full-scale tests in a commercial power plant and in a chemical processing plant. The technology was originally envisioned by Professor of Mechanical Engineering, Kripa Varanasi, to develop efficient water recovery systems by capturing water droplets from both natural fog and plumes from power plant cooling towers. The project began as part of doctoral thesis research to improve the efficiency of fog harvesting systems like the ones used in some arid coastal regions as a source of potable water. Those systems, which generally consist of plastic or metal mesh hung vertically in the path of fog banks, are extremely inefficient, capturing only about 1 to 3% of the water droplets that pass through them. The researchers found that vapor collection could be made much more efficient by first zapping the tiny droplets of water with a beam of electrically charged particles or ions to give each droplet a slight electric charge. Then the stream of droplets passes through a wire mesh like a window screen that has an opposite electrical charge. This causes the droplets to be strongly attracted to the mesh where they fall away due to gravity and can be collected in trays placed below the mesh. A lab test showed the concept worked, and the researchers won the MIT $100K entrepreneurship competition in 2018 for the basic concept. The nascent company, which they called Infinite Cooling, immediately went to work setting up a test installation on one of the cooling towers of MIT's natural gas powered central utility plant with funding from the MIT Office of Sustainability. After experimenting with various configurations, they were able to show that the system could indeed eliminate the plume and produce water of high purity. After the system was installed above one of the plant's 4 cooling towers, testing showed that the water being collected was more than 100 times cleaner than the feed water coming into the cooling system. It also proved that the installation, which unlike the earlier version had its mesh screens mounted vertically parallel to the vapor stream, had no effect at all on the operation of the plant. Video of the test dramatically illustrates how as soon as the power is switched on to the collecting mesh, the white plume of vapor immediately disappears completely. Power plant plumes are often considered an eyesore and can lead to local opposition to new power plants because of the potential for obscured views and even potential traffic hazards when the obscuring plumes blow across roadways. The ability to eliminate the plumes could be an important benefit, allowing plants to be sited in locations that might otherwise be restricted. At the same time, the system could eliminate a significant amount of water used by the plants and then lost to the sky, potentially alleviating pressure on local water systems, which could be especially helpful in arid regions. The system is essentially a distillation process, and the pure water it produces could go into power plant boilers, which are separate from the cooling system that require high purity water. That might reduce the need for both fresh water and purification systems for the boilers. What is more, in many arid coastal areas, power plants are cooled directly with seawater. This system would essentially add a water desalination capability to the plant at a fraction of the cost of building a new standalone desalination plant, and at an even smaller fraction of its operating costs, since the heat would essentially be provided for free. Contamination of water is typically measured by testing its electrical conductivity, which increases with the amount of salts and other contaminants it contains. Water used in power plant cooling systems typically measures 3000 microsiemens per centimeter, while the water supply in the city of Cambridge is typically around 500 or 600 microsiemens per centimeter. The water captured by this system typically measures below 50 microsiemens per centimeter. Thanks to the validation provided by the testing on MIT's plants, the company has now been able to secure arrangements for its first two installations on operating commercial plants, which should begin later this year. One is a 900 megawatt power plant where the system's clean water production will be a major advantage, and the other is at a chemical manufacturing plant in the Midwest. In many locations, power plants have to pay for the water they use for cooling, and the new system is expected to reduce the need for water by up to 20%. For a typical power plant, that alone could account for about $1 million saved in water costs per year.